This spectrum of the reactivity is something that you really want to remember. Sodium borohydride only can reduce aldehyde and ketone. Lithium aluminum hydride can reduce ester, even carboxylic acid. It can even reduce an amide and all the other things. It can even reduce the nitro groups and it's so much powerful, reducing many different things. But if you have now the ketone, then it really doesn't matter which one you use. Lithium aluminum hydride, sodium borohydride, both of them making alcohol. By delivering a hydrogen to there, then you just make an alcohol for both of them. Aldehyde, same thing. Both reagents will make the same product. So for those reagents, the functionalities, it's not a big deal. But when you have a carboxylic acid, that's the one that makes the differences. Lithium aluminum hydride reduce the carboxylic acid to the alcohol. Sodium borohydride, no reaction, nothing happens. If you have an ester, lithium aluminum hydride also reduces the alcohol. Sodium borohydride, no reactions. So clearly they're different. Okay, I normally get a question. Question is, why does it make an alcohol? Why not making something else? Why not making alcohol? Carboxylic acid makes an alcohol, aldehydes makes an alcohol, even those things that make an alcohol, all of them are making alcohol, right? Well, except when they're reacting with an amide, then it makes an amine, which we're not going to talk about right now. That's looking to. I have to save something for that. But at least I can explain why these things happen there. So I'm going to show you what happened if you're using lithium aluminum hydride reacting with acid. Hydride is going to be delivered there, and then that's going to make an alkoxy groups, as we just talked about. This is not the one that stays until the end and just get the proton, right? Because we have a leaving group right there. That's the same reason why the Grignard go for the reaction twice. Same reason. If you're using a lithium aluminum hydride, making an ester, you get an alkoxy group first, but that's going to come back, make the ketone, and kicking this methoxy out. So what you get in the end, you get an aldehyde. An aldehyde can react one more time with the lithium aluminum hydride. Lithium aluminum hydride is a 4 hydride to the liver. So it's a very efficient molecule. It can reduce a 4 carbonyl. So it can use a 2 hydride, and then now it becomes a nothing else to leave. And then just pick up the proton, then you get an alcohol. Because of these leaving groups there in the ester, that's the reason why you react twice. So you get an alcohol. Then what about the carboxylic acid? Why the carboxylic acid becomes an alcohol? Well, this is something that I'd like to tell you that. First reaction with the carboxylic acid with the lithium aluminum hydride is not this hydride attacking the carbonyl. Something else happened first. That is acid-base neutralization. This is a proton, acid. This is a hydride base. Acid-base reaction is the fastest reaction that people can ever record. So when acid meets with the base, acid-base neutralization is the first thing happening. This hydride get the proton, so you see a little bit of bubble comes out, that's hydrogen gas actually coming out. That makes an aluminum ester. It becomes a kind of an ester. Then you can expect that what happens. Then ester is this kind of another hydride attack, then you got the alkoxy groups there, but that's going to come back making carbonyl, kicking this aluminum oxide out. And then that becomes an aldehyde. It gets reduced one more time, then you get the primary alcohol. All together is consuming 3 hydride. But in the end, you get the same products. Alcohol here, alcohol there, all of them become alcohol. Why I'm showing all this step, you're going to see the reason later. Working those things out step by step, could be important for solving some questions. But anyway, just try to ask, using those concepts into the question, what would be the products if you reduce that one with the sodium borohydride? You see the two different carbonyls there, right? This one on the left side, that's an aldehyde. The one on the right side, that's an ester. Sodium borohydride can only reduce ketones and aldehyde. Then this one can be reduced, that one it cannot. So if you're using the lithium hydride, by the way, then it's going to be reducing both of them, right? So this hydride delivered to here, making alkoxy groups. Hydride delivered there, that's going to make alkoxy group in the beginning. But that has a living groups there. So this is going to come back and then kicking these methoxy groups out. So you get aldehyde in the intermediates. But aldehyde get attacked by the third hydride, and you're going to get the both becomes alkoxy groups. Now there's nothing to leave. Stay there until you add the water, they pick up the proton. So you get both sides becomes an alcohol. That side becomes an alcohol, this side becomes an alcohol. What happened to that? That just left out as a methanol. But methanol is a solvent, so you don't normally worry about it. On the other hand, if you're using a sodium borohydride, only the aldehyde ones get attacked, not the other way. So you get that becomes an alcohol, but that just stays as an alcohol. So clearly, depending on what reagent you use, you make different products. So that's the reason why we like to ask this question.
Same products that you get for
and we don't normally try not to do that because when you can do hydride, there's so much hydride in there, it can always go and reduce both of them. It's not the same, it's not the same control that you have with the even that was the controls are not very great either. We don't normally do that. But anyway. Speaking of the reduction of the carbonyl, it can be done other ways. What about the hydrogenation reaction, right? Hydrogenation means the hydrogen gas using the metal to reduce it. That can be done, especially the hydrogen gas with the nickel. Then that reduce the carbonyl to an alcohol. So you can reduce the carbonyl of the ketones and aldehyde, not an ester though. Ester or carboxylic acid also go that way. Ketones and aldehyde. And you can reduce that with the hydrogen and with the nickel, and you get an alcohol there. But the thing is, if you have some other part of the molecule having a double bond, that's going to be reduced at the same time. It's not selective. It's reducing the carbonyl, it's reducing the double bond. So basically, every double bond is getting reduced. So that is it. If you want to reduce all of them, this might be the way. Then you don't have to treat one by one. But what if you want to reduce that only? What if you want to reduce that only? Selectively reducing double bonds only, or carbonyl only, then what you want to choose? Well, double bond reductions, you know the way double bond, that's basically hydrogen gas with a palladium. Palladiums are more selective to double bonds. The platinums are a bit different. Platinums are, you can also reduce the carbonyl. That's why the platinums are, we don't normally use for that. Palladiums are, is much more selective to double bonds, carbonyl bonds. So that's why if you're using palladium with the hydrogen gas, then you can only use that. That's what we say. But what would you use if you want to reduce the carbonyl but don't touch the double bonds? So which reagent would you use? You talked about it. That's a lithium hydride or sodium hydride. So you have a choice of the reagent. If you want to use just the carbonyls only, this might be the preferred reagents. If you want to reduce that only, the palladium and hydrogen gas might be the way. If you want to reduce all of them, then you can apply this and that, or you can just do this and all gone. So it's basically knowing what your reagent does and choose basically.